Yeah, so I did solar car for like 10 years or so. And after I graduated with my PhD in electrical engineering from Oregon State, I went to Tesla for about 4 years. I worked on the stationary storage side, which is like Powerwall, Power Pack, as well as the car side, which is like Model 3 and the semi-truck. Learned a lot while I was there. I wish I knew a lot of what I learned there during solar car. After Tesla, I went to Chobe Aviation and worked on like the electronics for the electric airplane. I worked on like the inverter electronics and stuff that went into the nacelles of the engines of the airplane. I did that for about 1.5 years and did like nacelle electronics and BMS and other stuff while I was there. And then went to SunPower for about a year. And then now I'm at a company called Lunar Energy, where we're doing basically energy storage again. And so yeah, like Kale reached out and said, "Hey, like, you want to present?" I was like, "Sure." Like, I've got so many so many things I learned the hard way that I'm hoping that I can share with people. You know, like lessons that I learned, and hopefully like this helps people get rid of gremlins, because they happen all the time, and causing electronics gremlins is really a pain in the ass, especially if you're on the side of the highway. Like, that is not what you want to do. So maybe during this presentation, so like feel free to ask questions, and just like stop me if you have questions, and we'll also have a Q&A at the end also. Today we're going to cover like a lot of topics, anywhere from like connectors to protection devices to decoupling caps and communications and pre-work and everything kind of in between. So the first point of failure that my first solar car in 2008, we had this like solar tank basically, and we drove for 100 feet, and then the car stopped. And I was like, what the hell? Like, we just started on the start line, and then like we're on the side of the road within like 100 feet. It ended up being a connector issue. And so connectors are kind of one of the like major causes for failures. The connectors are a thing where like 99% good is not good enough, right? So there are like a variety of reasons why connectors would fail. So this is like a typical Molex connector you'll see like in a hard drive. And this is not something you want for a few reasons. One, this connector does not have a latch like this one does. So this can like fall out just from vibration. If you have to use a connector that doesn't have a latch, add a little bit of glue, like a little bit of like UV cure adhesive, to hold the connector in, so it does not come out. The other thing that can happen, and this is super bad, is terminals inside the connector housing can come out. Like terminals inside the housing, right, have a little like harpoon that like holds the terminal in, but those harpoons don't actually always work. Sometimes they don't fully engage, and so as you plug in, unplug, plug in, unplug, or when you just plug in the first time, the connector can touch, right? The terminals can touch, and everything works great because it's touching, but it's just barely encaged. And so you can see over here where this like this terminal has like packed out of this connector housing. And so a way around that is something called having terminal position assurance, or TPA. So a TPA is a little piece of plastic that you shove into the back end of a connector, and these little like TPA fingers keep the terminals in. I had to fly to LA once to someone's home, and because their power wall was not working and their house didn't have power, and I was like, what the heck's going on here? And I took the connector and I started tugging on the harness, and one of the like pins pulled out. And this was something where it passed the end of line checks, where it did the functional check, everything was great, because the connector was, the terminal was touching, but it wasn't fully engaged. And so you can have instances where, especially during, in a car with poor suspension, which is all solar cars, where the vibration causes terminals to disengage. And what caused my solar car to stop was I had this RJ45 cable. I used an RJ45 as my throttle harness. And what happened was, like, we hit like a pothole or something, and the vibration caused the throttle to momentarily disengage, and the inverter saw that there was a glitch in the throttle, and it was like, oh, I'm gonna shut off because I don't trust that throttle anymore. And then of course, if you power cycle it, it works great for a little bit, and you hit something again, and it fails again. And so certain connectors to avoid, like connectors with no latch, avoid those. These like 0.1 inch like header terminals, which is like all of your Raspberry Pis, all of your Arduinos, avoid them completely. These terminals absolutely do not do well under vibration. Some people try to use this in an electric airplane, and it works great on the bench, but when you put it in the nacelle of an engine on an airplane, and you turn on the propellers, it stops working momentarily and causes tons of problems. These like rework or these like prototyping jumpers, super tempting again to use, do not. If you have to use like an Arduino or a Raspberry Pi where they have those like 0.1 inch headers, like solder them in. If you just plug them in, it will work most of the time until you hit like a little like thing when you're changing lanes, or when you go over rough asphalt or something. It's just like, and you'll have a glitch and you can't reproduce it, and you don't know what the problem is. And it's these like these connectors are a huge contributor to that. Does that make sense?
Yeah.
Okay. Cool.
Yeah.
Cool. Yeah. So yeah, avoid these. Get like, so my favorite lines actually are the Molex NanoFit, MicroFit, and MiniFit with TPA. They have two families in Molex. One of them have TPA, one of them do not. The ones with TPA, they're great. Avoid the ones without TPA. Okay. Also, I'm sure a lot of you are familiar with these, the Anderson power pole connectors. They're used all over solar car. They're not waterproof. I think they have like watertight coverings that you can potentially use. For like super high current connections, like these 350 amp connectors, there's kind of two ways to reliably connect them. One is to use this like pretty expensive, crimper to crimp this terminal. The other way is to use a blowtorch and just like put the terminal in a vise, put a blowtorch on it and start melting solder, and then stick the wire in. Like things that don't do good to secure them, like hammers. I've done it. Like I needed to crimp something, I didn't have a crimp, so I used a hammer to crimp it. Vice grips, not good either. You know, like something high current, you do this wrong and it can have high series resistance and start a fire. It can fall out, and you'd be very sad if one of those things fell out in your car. And yeah, so for the smaller connectors, you use the proper crimpers, and for the big ones, like get a good crimper that is like designed for this, or just use a blowtorch. AEC-Q. So this is something I didn't learn until I was at Tesla. When you're designing a PCB, like when you go on DigiKey, like there's often a filter where you say, hey, I want like automotive components or automotive AEC-Q 100 or AEC-Q 200. And what it means is if you filter by these components, these are components that have been specifically tested in the like automotive use case for vibration, temperature, and like reliability. So it's like tested for thousands of hours under like thermal cycling and humidity freeze and all of that. So like, why would you choose these? Well, so for example, like I selected a relay for the prototype Tesla Semi, and they're like, oh, that's not AEC-Q. Like, okay, what's up with that? So if you have just like a normal electromechanical relay, right, and you put that in your car, and let's say you close that relay, you can hit something on the road, and the vibration from that like impact just from the road can momentarily open that relay, and you'll have a glitch and be like, hey, what happened there? And it'd be really hard to produce. But you know, things like relays, semiconductors, and passives like capacitors and resistors, and connectors, like choose AEC-Q when possible. Like go with non-AEC-Q only when you have no other option. And especially with like relays and like capacitors, definitely choose AEC-Q like when you can. One of the most vulnerable components in cars, and you know the most overlooked, is decoupling capacitors, which are little caps you put right next to a like integrated circuit to like smooth out the high frequency noise coming from the power rail. They're used everywhere. People just use them because like you have to, and they're everywhere, right, on a PCB. And one of the things we did at Joby was do like a failure modes and effects analysis on the plane, and said, okay, what is the component that can take this plane out of the air? And we identified that this decoupling cap is the most, like the biggest vulnerability the plane has, because it's like hundreds of thousands are used on a plane. And if you have a short in any of these capacitors, it brings down the entire power rail of that PCB. So like if you have a 3.3 volt rail and you use this cap on all of your, you have a cap on like every IC, right? If one of them fails short, it will bring down the entire PCB, and it could fail short intermittently and cause glitches. And just use AEC-Q for these. They're also rated for high temperature, either 85C or 125C, and you can get to these high temperatures when you have a component that's in the sun, and then you add additional heat to it. So like all of these like AEC-Q components are designed to or they at least give you a first order defense against the conditions you'll see on the highway in cars. Capacitors and resistors. The rule of thumb is that like when you choose certain components, there's all these different sizes. Don't exceed 1206 unless you absolutely have to. What happens is on the road, there'll be like vibrations and your PCB will like flex up and down. and a board that flexes with a part that's bigger than 1206 will tend to crack. There'll be a force on the capacitor that causes it to crack. If you have to exceed 1206, like use FEA, like ANSYS Sherlock, or like make sure you put like holes for mounting feet around that heavy component so that it doesn't break. The other strategy to get around this is to put resistors and capacitors in parallel and series to get the value that you want. In the early Roadster days, this rule was not followed, and Tesla found out the hard way. Like, do not exceed 1206 for both resistors and capacitors. It's just like not a good thing you want to do. Like, you can do it, but like to ensure reliability, like you have to use like FEA. And again, like this failure will not be like a hard failure. Sometimes it'll just give you a glitch, and then it fixes itself, because when you park the car, the vibration stops, and now the part that's broken like touch each other again, and you check it and it's just fine, and then you drive again, like 2 hours later it comes up again, and then it stops, and it's just like super annoying. All of these failures take a lot of time and a lot of data to like properly root cause, and both of those are not things you have during a competition. Overcurrent protection, so fuses, right? Fuses are actually a cause of field failure because a lot of them suck. There's kind of 3 types of fuses in general. There's the like thermal fuse. They're cheap, they're great. Cons, they have a big trip range based on temperature. So say you get like a 20 amp fuse, you get it hot, and you might be able to, you might have to derate that by 30%. So now all of a sudden it trips at like 16 amps. You get it cold, and all of a sudden it doesn't trip until you're at 25 amps. You have a fuse holder in this thermal fuse, and that fuse holder is not holding it right because there's vibration. You've replaced the fuse a few times, it got dirty, and now there's high series resistance on that terminal, and that terminal starts to get hot. And then you put that hot terminal, which then raises the temperature of the fuse, plus like sun load, and all of a sudden your fuse blows for no reason. Ptc Resettable Fuse, they're still like cheap, and they're resettable, but the trip range is still like based on temperatures, including the board geometry. I once had a PCB where between 2 revs of the PCB, my trip current changed. And what happened was I had a PCB where I had a surface mount PTC positive thermal coefficient fuse that was sitting on the board with just a trace going away from it. And I changed that trace to a copper pour. And then I was just going through testing. I was like, wait, like, why is this fuse not tripping? The fuse current changed by like 50%. And then I realized, oh, it's a thermal fuse. I put a giant heat sink on this thermal fuse, which is super annoying, right? Like you don't want your trip current to change by like, like 30, 50%. So more recently, the thing that's come out is called eFuse. You guys probably have already heard of it at this point, but they have a precise trip point. They're resettable, and some of them even have current monitoring. They're slightly more expensive, but they're like very much worth it. The trip points are programmed by like resistor values. You can see how much current is going through them. So then like you can send that back to your microcontroller, and you can have a plot of that. And if the current on a particular line increases somewhat, then like you might be like, oh, something's up with that, right? And people have taken apart the Tesla Model 3, and like the whole car uses e-fuses. They also have a very fast trip point. So like they trip like under like 10 milliseconds or so, like on that order. And TI makes a great family of e-fuses, like this TPS 25982 is a good example of that. And this is something that I would recommend that people use in their car. Like forget PTC and thermal fuse and just use an e-fuse. It's just so much better than everything else out there. Also, fuses, you got to put the fuse in the correct spot. Putting them in the incorrect spot can cause issues, right? You fuse at the source of the current. Otherwise, the fuse doesn't do like as much good. If you have this, fuse and you put it by the load, can you guys see? Oh, sure. I'll get a little pointer. Does that work? There. Yeah. So if you have this, source and load, if you put the fuse over here, well, if you have a short on the load, well, that still helps. But if you have a short on the wire, well, now you're going to be in trouble, right? And here, your fuses still have this like nasty D-rate curve. This is a like fuse curve like I pulled out of little fuse. And for solar car, you're more concerned over here because you're going to be on the hotter side of things. And you can see the D-rate goes back to like 30%, right? This is that 70% nominal. And so you kind of always, if you have to use a fuse higher currents, like go a little bit higher. The way you fuse this is you select the fuse to protect the harness. So your harness has to have like an ampacity that has a certain factor of safety above what it takes to trip this fuse. So if you have like a 10 fuse, get like I think 14 gauge will go up to 15 amps. I think that's true. I think for houses at least. So like make sure the ampacity of the harness is higher than the fuse, because otherwise, if you have a harness that starts with the insulation that starts smoking before the fuse trips, you'll be very sorry. Other types of devices, over voltage protection. So over voltage protection is actually over current protection with a device that is open circuit below the breakdown voltage and closed circuit above the breakdown voltage. There's kind of two in general. I'm sure there's more out there like gas discharge tube and so on and so forth. But the two that's common is TVS diodes, which is a more useful for like low voltage protection, and MOVs, metal oxide resistors. They're more useful for higher voltage protection, but they have a less precise trip point. They're also self-sacrificial. They'll have an energy rating. So the way you use these is you put this over voltage device in front of your load with a fuse. So the way that this works is, let's say one of your solar car teammates decides to plug the array umbilical in incorrectly and plugs in the not keyed array wire into the same connector as your body controls for the umbilical, and sends like array voltage into your electronics, which absolutely happened one year. What happened then is if you have like 100 volts on this source now, what happens is this TVS will activate and say, hey, like I'm going to short circuit and become like 0 ohms effectively. Well, then what happens is this is going to get hot and start to get hot, but like at 0 ohms, electricity, it flows the path of least resistance. People say that, but it's actually true. And then so what happens is all energy goes through this TVS instead of your like fragile electronics. And then before this TVS or MOV blows up, you blow the fuse upstream of that, because the fuse now gets a high amount of current and it gets blown, and then your circuit is protected. You know, like for like solar car, like over voltage events happen a lot more often than we would like to think. Like, hey, you're charging something on the side of the road, or you get this like high voltage power supply you're testing, and then someone like walks by and knocks over your test leads, and your test leads go flying, and they go across your electronics, which again has happened before. And you know, like if it hits something, you want them to be protected. ESD. So another source of gremlins is electrostatic discharge and surge. You go up, you skip your feet, you touch something, you get a shock, right? Sometimes you feel it, sometimes you don't. And the thing works just fine. You test it, it works fine. It works great. You test it for, you use it for like another week or 2 or 3, it still works fine. You go to the race, you go through scrutineering, it works great. You're like in the middle of Kansas, no cell reception, and it has a glitch, and you pull over, and you're like, what's up with the glitch? And you can't find it. It works fine now that you pull over. You drive again, and then it works fine for a while again, and then you're in the middle of like Nebraska, and it fails again. And so what happens with ESD is that it causes like really intermittent failures that's super, super hard to diagnose. And only when you have like figured out, oh, maybe it's this, you know, like microcontroller or ADC, and you like, okay, like something's wrong with this, and you send it out to a test lab, they cut it apart, they use a like a electron microscope, and they figure out, oh, PS, it's like an ESD thing, and it costs you like $10,000 for this like test, and you don't ever want to do that. So how do you protect against that, right? So most ADCs or GPIOs, they're high input resistance. Like this is typically like 10 mega ohms or so. So it will not care if you put like a 1 to 10K series, like 1 to 10K series limiting resistor here. And then what happens is, you tie this to like a harness or a button or something where a user can touch, or it's a harness or something, right? Like you're trying to protect this input from ESD or high voltage. So let's say this is a 3.3 volt microcontroller, and this VCC here is 3.3 volts. And let's say you put like 5 volts on it. Well, what happens is 5 volts comes on here, it goes through this current limiting resistor, and the 5 volts, or 500 volts or 5,000 volts with the ESD, it sees this diode, and it sees 3.3 volts on the other side. And then what happens is it'll start to conduct this energy into the power supply rail, then it gets safely consumed. If you have like an ESD event where you're touching it with like negative 1,000 volts, say here, this thing comes in and says, oh, it sees this 0 volts here, which is less than like negative, which is higher than negative 1,000. And what happens is you actually suck energy out of the ground through this diode across this resistor and out to like the ESD source. If you actually have to protect this against like active high voltage, like, oh, let's say you have a harness where you have high voltage wires and low voltage wires in the same like housing, and you might be afraid of like cables getting like scuffed up and so on and so forth. This will also help you. Like if you have a properly sized like current limiting resistor that can dissipate the heat, well, now let's say you put 100 volts or 200 volts on here, right? And this is 3.3 volts. What happens is you drop like that high voltage across this resistor or two of them for clearance and creepage reasons. And then the current goes through this diode and up into your power supply rail, and it's protected. If you put in like a 0 to 3.3 volt signal, right, they'll go through this current limiting resistor. This is 10 megaohms, so it won't care. And 3.3 volts is the same voltage as the supply, and it's above ground, so like nothing happens, right? So anything between between ground and VCC, these diodes will not activate. When you go above and below the ground and VCC rail, it activates. One thing to be careful about for ADCs is that you want to make sure you get a low leakage diode, like a BAT45. These actually come in packages where there's 3 of these feet, and they're all like packaged so that like it's actually 2 diodes in one package. It's designed just for this purpose. Oh shoot, it's 10:39. Like, I know we started a little bit late. I'm gonna go through this a little bit faster because we might be running out of time. Decoupling capacitors. Decoupling capacitors is a thing where capacitor is a variable resistor with respect to frequency. The higher the frequency, the lower the resistance, and you use to filter out noise. You want to put the decoupling capacitor so it's like the current goes through it, like here. This is the only thing that's correct, where you have ground and VCC and the current goes through it. If you do anything else here, the decoupling capacitor doesn't do anything for you, and you might have gremlins. Also, you want to make sure your caps are like rated for the applied voltage, which for the actual like voltage with at least some like headroom. So if you have like a 12 volt system, get at least like 16 volt rated capacitors. High side switch. So say you want to turn something on and off. You can use a relay, you can use a MOSFET, or you can use a high side switch. A high side switch is something that is current limited. It has current sense and feedback. It has like temperature sensing. It's heavily used in modern electric cars, and you don't have to deal with with like gate drives or anything like that. So like high side switch has like it's like effectively a fuse and a switch, and it has all the current sense in it. So like you can have like a horn or a blinker or something. This is so much easier to use than a MOSFET. Yeah, and this just like shows the insides of it, and like you can even have current sense feedback and temp and voltage sense, and just so much more superior than a transistor alone. Watchdogs and power on preset. I think if you use Arduino or whatever, they'll already have this. But the issue is this: like when you plug something in, the voltage on your microcontroller starts at 0, and then it comes to VCC, right? There's going to be a transition period in between, and what happens during this transition period is your microcontroller goes insane. Like it could be that the memory, especially in your microcontroller, gets like filled with random values. So imagine if you had your code and all of your variables were like initialized to crazy values. You just don't want to have that. So what you can do is you can get a chip that monitors this voltage, and once it's stable, it hits the reset for you. The other thing that you can have, right? Like how like when you're using your computer and your computer freezes, you restart it. Well, the same thing you can have a similar thing for microcontrollers. It's called a watchdog, and the way you use it is in your code, you toggle a pin like on and off, on and off. and that pin has to be toggled with a certain frequency. Like you have to like toggle it from 0 to 1, 1 to 0, like 1 second or twice a second or something. And if this chip does not hear from you, it means that your main code is frozen, and it will hit the reset button for you on its own. This chip from Analog Devices actually is a power on reset and Watchdog all in one chip. But be careful to use these in certain applications like BMS or inverters. Like sometimes if you reset the inverter while you're on the highway, you can cause problems like an uncontrolled regen or something. Like be careful about where to choose them, but in general, having them is better than not having them. Yeah. I mean, I did this 10 years ago, so things probably have changed since then. But at the time, a lot of solar cars had like cockpit displays, like that were like 2x16 LED, or like LCD like displays for speed and so on and so forth. And the horn, the blinkers, everything was a mechanical switch. Like that's what I had. And so if you have a lot of switches, it's just like and switches and LEDs and whatever, there's a fair chance for like switches to fail or the soldering of switches to fail. What we did in 2010 was steal fair and square from Tesla and changed our like cockpit controls to an all touchscreen interface. So you can have your blinker controls, your horn, your speed indicator, your rear view camera, all of that put on like a display that is perhaps on your steering wheel. Like these cases, you can get like a tablet or a Raspberry Pi or some sort of single board computer where you can just have virtual buttons instead of actual buttons, because virtual buttons are way more reliable. Also, you can it allows you to redesign the user interface without doing electronics hardware work. The additional thing is if you pick like a tablet that is easily had at stores, like let's say your tablet breaks or somebody hurts it or something, like somebody accidentally dropped a hammer on it. If you're on race, you can go to like the nearby like Best Buy and get a new tablet where get something that is purchasable in stores, so that when you have a problem, you can just find the replacement component in a store. Communications. So there's a variety of communications systems you can use. Like people have used like UART, USB, RS-45. CAN, controller area network, is actually one of the most robust systems out there. It's differential. It's used in cars, like unanimously, like throughout the entire industry. Like CAN is the thing that people use. CAN and sometimes LIN if you're trying to be cheap. But the cool thing is it's highly robust. It uses 2 wires. And it's highly compact. So the format is like address, date, the length, the data, and the CRC. So for example, you'll see like an address of like 450, and like length 8, and then you'll see like an 8-bit packet of data afterwards. And the way that this is encoded is like you can have like things like like your speed in the first like 8 bytes, and then maybe the temperature of your inverter for the next 8 bytes, and so on and so forth. You can actually even like split up the frame of a byte and like use like bits within a byte to make things more compact, or you can span multiple bytes for information that is required, that is, that requires more than 8 bytes. The cool thing about using CAN is that it enables debugging a lot. So as soon as you use the CAN format, well, now you can use all of the tools available to card manufacturers. So Pcan Explorer or the program Canopy, like, it's the stuff that you can use. So you get these like Pcan dongle or whatever, you can plug it into your CAN network and you plug it into a computer. And then the cool thing is you can take everything on your CAN bus, you give it a translation file, and then you can start doing things like plot the data over time and record stuff. And it does it in real time. And then, like, if you're trying to debug your car, it's so much easier to have like all of the variables and stuff like that plotted on the screen. But it's really only available for CAN. If you want to debug other stuff, you might have to like write your own debug tools. But if you use CAN, like, it's available to you immediately. Okay, so electronics architecture. The way you design your car's electronics architecture can help you can affect the reliability of your car, and also affect field service. So in the first gen, second gen, like Tesla Model S and X, they use this thing where, they have a smart device for everything. So you have, you get your cockpit controls, and then it's hooked up to the horn. The horn is a microcontroller with like a CAN transceiver, and when you hit the horn button, the CAN transceiver sees that you've commanded the horn to activate, and then it activates the horn. Same with the blinkers, right? This is a microcontroller that is on CAN, and then you give it a command over CAN, and then it like closes a high side switch to turn on the blinkers, right? So the advantages of this architecture is that it gives you an easier like thing for field service, because what you can kind of design is a generic like microcontroller with a high side switch or a relay, and have the same hardware be copied everywhere in your car, and then all you do is change the code that goes in them. And say, like, you're on the road, you have like in your hip pocket like 100 of these things. They're all over your car. Now, one of these fails for some reason, like, oh, like I didn't protect the blinkers well enough against rain, and it's raining, and like one of these like got wet. Well, you can just pop that module out and like flash it with the proper firmware and plug it in, and you're on your way again, right? It's slightly higher cost because every device has a microcontroller instead of not. So for cost down, you can have like a centralized like PI controller with the big like PCB with a smart microcontroller and everything, and have like wires going out to each of your devices instead of like CAN plus power. The advantage of this is like it's generally like lower cost, but it's more wiring and your PCB is more complex. And so I actually recommend, like I don't strongly recommend, but I generally recommend like adopting an architecture where your PCB is super simple. It's just like microcontroller and a switch. And then like if it fails, who cares? You have 100 more, just replace it. Whereas this thing, like pull all the harnesses off, open the shell, replace the PCB, right? It's just a pain in the ass. And for these things, like you can make these modules pretty small. And what our university did, and this is not the thing that like you can do this, but you don't have to. But like we got the PCB so small that it fits inside like a 2-inch PVC pipe. And what we did was we just like put the PCB in the PVC pipe, and then we put like foam on either end to like close out the to do like rough waterproofing, and it also allows the wires through. So like enclosures become a little bit easier, I think, when you have like very small PCBs that you can enclose pretty easily. But like you can go either way on this. Let's say you get a PCB back and it doesn't work perfect the first time. Shocker, right? Like that always happens. When you do rework, the thing that I found to be helpful is actually using transformer wire, like thin gauge transformer wire. Like you can go up in gauge if you have to, but like a 30 gauge transformer wire that you can get on like Amazon is really great, because the way you do the pre-work is, you like slice a trace, and then you just like take a blade and scuff off the insulation on this transformer wire, and then you solder it. Just so much easier than like stranded core rework wire. Sometimes you get a PCB back, and it costs you like a few thousand to get a spin of PCBs, right? And it's like badly done. Like the error is so bad that the rework is going to be really hard. So what you can actually do is make these quick turn PCBs that is like a patch type PCB. So here, I had the transmit and receive side of an isolator flipped, and like, well, crap, like this is going to be impossible to pre-work. So what you can do is just get like, you can design a PCB that sits on top of the old PCB that you have that has all the pre-works on it, and then you solder the two together, and then you glue this with like this UV cure glue. Like this is super nice. This is a glue where you just get this on Amazon. You squeeze out a little bit of glue on one side, and then expose it to UV light. It cures in like a few seconds. It's way better than super glue. Use this glue to like tack down your reworks. This is way easier to use than super glue. It doesn't get everywhere. It cures quickly. It cures when you want it to cure. If you get it in your hands, like you can wash it off. This is really nice. Let's say you have to rework a harness. Some of you have probably seen this already. This was actually on my Facebook ad. I was like, holy crap, this is amazing. What this is solder heat shrink splice connectors. This has solder on the inside, along with like two waterproof like blockers here, and you put the wire in side by side, and you heat it with a heat gun or a lighter or something, and it melts the solder, solders the two wires together, and heat shrinks it and makes it waterproof. Also, like when you are making harnesses or you're using E-tape, make sure you use automotive grade E-tape. Like Ptc is a good brand for that. When you use like normal E-tape, what happens is the E-tape gets hot and then it gets sticky. And when you untape it for anything, there's just glue everywhere. So get these high temp automotive E-tapes so that when you do your harness, like it's not sticky everywhere. Lastly, you want to have fixtures for electronics testing. So one of the things that our team had trouble with was, the electronics was always at the very end because you didn't have a car to put the electronics on. Well, what you could do is do all your electronics and make all the harnessing with the correct lengths and everything, and test it on test bench. And it allows the electronics team to be unblocked if the car's not done, and you can do all the testing, all the debug on a workbench, and then you can transfer known working hardware and firmware to the car, right? Also, stuff will fail anyhow. So you want some good diagnostics tools. One of these is a device called the short sniffer. This is actually something that my father-in-law created. It has saved me so much in the past. So the way it works is electricity follows the path of least resistance is always true. What the short sniffer will do is on these positive and negative leads, it injects a low current AC waveform that's audible. So like when you put these clips on, it'll inject like a 1 kilohertz signal or something, like 1 kilohertz electronics signal into the circuit that you're trying to test. And then you have this like antenna that you can wave around the PCB and pick up where that that sine wave is flowing. So if you have a short circuit, what happens is that like sine wave will flow through to the short circuit spot and then come around. And so you can like wave this antenna like at the start point and follow the current around your PCB, right? And you'll find the components that's shorted. One time, there's a short in a harness on a Tesla semi, and there's like 50-foot harness, right? And we're like, well, crap, like we're in trouble. Like we know these two wires are not supposed to touch. It's 0 ohms. That's great. But we don't know where it is on this like 50-foot harness. And so you unplug the harness, and then you plug this like short sniffer on there, and you hear the tone through the harness. And you hear it, and at the spot where you stop hearing the tone, that's where the current makes a U-turn, right? And that tells you the spot where the harness is shorted. We had a time when we lost isolation on our solar car's steering wheel. I mean, on our solar car's like low voltage electronics. We couldn't figure out like where the short was, but we know we lost isolation. So we took like this short sniffer, we plugged it into the car, and we started waving it around. And it turns out that the short was near our steering wheel. Our like tablet was mounted on this carbon fiber steering wheel without an insulator, and it scuffed through the steel packing. The paint on the back of the like display scuffed through, and now we shorted the low voltage ground to the steering wheel through the tracking pinion into the car. And like, and the way we were able to find this was we were able to hear the tone through the steering shaft, up the steering column, into the steering wheel. Like, what the hell? And you take the display off, and the tone stopped, right? So if you have a short or something, like there's not many tools out there that can do this. A Fox and Hound is a tool that's also commercially available that can help you do this. And a Fox and Hound will work with like single conductors in addition to 2 conductor shorts, but it's not as accurate. Like the resolution is not as good. Like this will help you find like a shorted like capacitor on a PCB. The other thing you want to have, like absolutely, is a fluorescent infrared camera. You can get these like infrared cameras that attach to your phone, and it allows you to see heat. So oftentimes a broken component on a board will get hot, and a lot of times, I guess, like I used to just use my fingers to figure out like what's hot, but if this is your BMS, you can't do that. So have a fluorescent camera. They've gotten down in price like a lot. So this is like $200-300, like super worthwhile to have. And that's it. Any questions? Complete silence.
I was curious, would you be willing to post your slides to us?
Absolutely. Absolutely. I'll put it on I'll put this on Discord. Absolutely.
Thank you.
And you'll,
Sorry.
yeah.
You mentioned soldering for the high current connections, and I was wondering what your opinion on what was on for hydraulic crimping of those connections.
Yep. Yeah. Hydraulic crimping is perfectly fine if you have the right die. And at least when I was doing this, the hydraulic crimping was pretty costly. But if you have one, great, use that.
Thank you. Sorry.
No, absolutely.
Just a real quick question about the eFuse.
Yeah.
Is it like a high current rated microcontroller, or is it like an actual integrated circuit like packed around a fuse?
Yeah, it's an actual integrated circuit.
Okay.
And you can get these up to like 20, 30, 40 amps.
Okay.
And they're like very small footprint.
Cool. Thank you.
Yeah. Great questions.
Oh, also, sorry, on the TPA at the very beginning, you were showing like one of your, I guess, diagrams. It's like an insertion, it looked like. Was that implying that like you can like buy TPAs like kind of like on their own, or is it always going to be built into the connector?
They will always be associated with the connector family.
Okay.
Yeah, you can't buy TPAs for a different family. Like they're always, yeah.
Cool.
Oh, and also like get de-pinning tools for these things too, because sometimes you want to pull a terminal out of a connector, and you know, like you don't want to repin the whole thing. Get like de-pinning tools for these things.
Cool. Thank you so much.
No problem.
I had a quick one about using a tablet as like a steering wheel interface.
Yeah.
Would you have to power that off of the car's battery, or could that be independent from the car?
So we powered it with like an auxiliary 12 volts. I don't know what the current rules are, but like for non-critical systems, we were allowed to use like a rechargeable, and we used NiCad at the time. Yeah, I believe we had like a pretty big like NiCad on there.
Somebody in chat says that based on the current rules, I think it would have to be off the main bus.
Yeah.
So.
And yeah, but which makes sense now. Today's like tablets are also like pretty low in power. They're like 3-4 watts really. Like 5 volts, 1 amp can charge a tablet, right? So like in my personal opinion, like that few watts don't really count in my mind, but we also didn't get first place, so you know, like yeah. All in all though, like the solar car, while it's all consuming in your life right now, really is a tool to educate students for the future. And having this kind of, having this kind of interface allows students to be exposed to things that they're gonna have to do in industry anyhow. And Tesla will definitely appreciate a car that has like people have with experience that with like digital cockpits. But yes, that's a good point.
I have a question about the electronics architecture, the one with like the Tesla.
Yeah.
I'm just wondering why. So you said first and second gen is kind of like very modular versus the future ones are. Why did they decide to switch, especially if I think what you said preferred the first one, right?
Well, so it's preferred for like field service, but it's higher cost. And Model 3 was all about lower cost. And so once they were able to make a car and make it reliable and make it and they understood what was causing the failure, they were able to cost down a lot. And so the Tesla Model 3 has 3 body controllers. There's one under the hood. There's 2 on either side of the wheel well, actually. And in terms of cost, the Tesla Model 3 controller was just way cheaper. It was like less than $10, honestly. It was really cheap. And because Tesla had more time to do this, they were able to put the time in to do the cost down to produce a cheaper car. And once that was successful, I'm pretty sure the new S and X has now the same architecture because it doesn't make sense. But for solar car, where you're making a one-off prototype, I think in general it makes more sense to do a more modular architecture. For more mature teams with more history, it actually might make more sense to do iterations of a controller that looks like this, where you can reuse and improve on the previous controller that your car had. But for us, everything was new and everything was not always working. And so we found that this architecture helped us a lot.
Thank you.
No problem. So actually, if we have a little bit of time, I think the next thing starts at 11:30, perhaps. We can go into some additional stuff if people want. I have a couple of things in the appendix. One of the things you kind of a thing that you can have in your car is an isolator. These isolator chips, they help break ground loops as well as for functional safety. You usually use an isolator between your high voltage BMS and low voltage microcontrollers. So this is a TI ISO 6000 series chip where this is 3 in, 1 out, and this is designed for SPI, SPI. When you do this, you also have to make sure the power supply is separate, or else you don't have isolation. An SN6501 is a typical thing that you can use along with the isolation transformer to get you isolation. So this is something that you want to use in your BMS or between things that you suspect have ground loop issues. I thought that I might not have enough time, so I put stuff in the appendix. MOSFETs, honestly, I would not use these days. The high side switch is just so much superior in every single way, except for cost. But solar car, who cares? It's $1 versus 10 cents. You don't care.
What was superior to the MOSFET? What would you say that was called?
Oh, the high side switch. So this from TI, this TPS1H. This is effectively a electronic relay. So when you put a high on the enable, it connects VBB to V out. It has current sense, so this S and S line has an analog voltage that is proportional to the current flowing through here. You can also choose you can enable diagnostics, and you can select what is output on your diagnostics. So this ST output, if you could be what it could be voltage sense, or it could be the temperature of this thing, depending on what you choose here. And this chip is tiny, and it's cheap. And if you want to turn on a horn or a blinker, use this. It's just so nice. It's so nice. You can use a MOSFET also, but like it doesn't have built-in current sense. You have to add, like you have to have like pull-down resistors and snubbers, which you still have to have. But you gotta like choose this wisely, which you still have to do. But like, this does not have overcurrent protection. It doesn't have current sense. It doesn't have temperature sense or anything. And for high side switch, you have to use a gate drive also. So like this has everything you want all in one chip. Like gate driver is all built in and has energy and current limits and thermal shutdown. It's just so very nice. And this is a chip that you can use to like turn on your blinkers, turn on your headlights, turn on your horn, turn on your fans, like whatever you want. Like this chip is just so nice for that.
Yeah, that's super cool. Thank you.
No problem.
So I was wondering your opinion on CAN terminations. Currently, we're running on the car that I've currently been working on. I'm more fault tolerant or like a star termination scheme rather than a line to line. And I was wondering what your opinion was on that.
Yeah, so stubs, right? Like star topology is possible. There's some rules of thumb for that. Like I think it can't be over 1 meter or something. And it affects your CAN speed also. So like if you want to go faster with CAN, your stub length is there's more restrictions on it. The thing that I would do is build in so you can use a star mechanical topology with a loop electrical topology. So on your board you can have CAN in and CAN out. So 4 wires instead of 2, and your harness still looks like a star because you have 4 wires going to an ECU. So 2 wires in, 2 wires out, right? And that's what Tesla ended up doing, was just like a star configuration, star configuration, but is the daisy chains built into the PCB itself, and that's what like a lot of car manufacturers do.
Is there another name for that topology? Because I've tried looking it up. This is sort of something that was passed down to me, and I don't really understand how to. Yeah.
Well, in terms of like the star topology, like issues, look up CAN stub length, STUB, like stub length. You can do it. Because CAN has built-in like error checking. What will happen most of the time is you'll just have slower data transmission. Because what will happen is you'll have an error, and the CAN chip will see that it has an error, and it will ask the transmitter to resend that again, and it'll do that, and most of the time it'll be invisible to you, unless you have like PCAM or whatever, and you can see what the timing errors are and so on and so forth on here. Like it'll work most of the time. If you have safety critical messages, like Tesla was using CAN to, for all their like traction control and ABS and stuff like that. If you have to retry, that will not be okay. So, yeah, like I would not recommend stubs if you can help it. And the easy way to do that is just to have like a electrical daisy chain, so that your harness still looks like a star, but it comes in and out. Does that make sense? Like I wonder if I can like draw that or something. I don't know.
Yeah, I think I've got what you mean.
Yeah. So, okay, cool. That like you'll have like 2 CAN wires coming in and 2 CAN wires coming out, but it still looks like a star.
like the best illustration of this is how Tritium does their CAN stuff with their motor controllers and their driver controls. Essentially, the car channels are duplicated, so you can connect into either one. So it makes it easy to daisy chain.
Yeah.
So you can
Absolutely.
look at you can look at their designs if you want to look to see how you can implement this daisy chaining technique.
Yeah, and you can even put everything onto one connector so that you don't have a lot of like connectors to deal with. I think like, for this architecture, you can implement this architecture this way, mechanically with 6 wires going to each thing, where it's 2 power and 4 data, 2 in, 2 out.
Would you advise maybe using like T-junction M12 type connectors with 5 pins? Because you can kind of get those that plug into one.
I'm actually not familiar with that connector, actually.
Let me see if I can find one.
Yeah, and we can put it on chat and we can all take a look. Absolutely. Let's see, how do I do a chat here? Funny thing, like during the pandemic, I have not used Zoom like so much as like, oh, the chat. I didn't even see that because I use like Teams and Google Hangouts, stuff like that. Cool. Okay.
I've just
thank you.
I've just given you an example link.
Oh, these like yeah. So
I mean, the only reason why we've kind of moved to these connectors is we've tried running with like microfit CAN connectors and they fail quite a bit. I mean, that has been looking at our races over the last 5 or so races. All our electrical failures were all connector related.
Yes.
And so we've kind of moved to only using automotive connectors. So we're using HDAC or Stack 64.
Yeah.
And
good idea.
And we've kind of also
absolutely
with built-in PCBs we're into these connectors just because we want to know that if the connector is plugged in, it's plugged in, and that all the cables are overmolded and we don't have to worry about crimping quality, because crimping quality is really important.
Yep,
trying
agreed.
to crimp with like a piece of pliers, it'll work when you're testing, but once you're on the road after driving 10 miles,
absolutely
it happens. And
yes, you need to correct, you need to use the correct crimping tools and crimp correctly. That's a great thing I didn't speak about today. One thing about, so like you mentioned like Molex microfit, I completely agree with you actually. Microfit connectors fail, they suck. I put them on here. Why? Some of these have TPA on them, and it's the Microfit 2.0 or the Microfit 3.0 now, I think, that have TPA that makes them, I think, okay. But I think these are superior. LEM also makes really good connectors, but they're hella cheap or hella expensive. Like, but they're really good also. Yeah, I think these are great. Like I haven't seen the terminals on these, but they probably have dual like terminals for each, dual like little like kinds for each terminal.
These, I mean, I've seen these being used in like industrial equipment, like in mining type stuff, and the CAN bus usually transmits using similar.
Yeah, I bet these are fine. Yeah. Good stuff. Here, I'll share this link. I'll put this on a chat here for now. There's a lot of good connectors out. Yeah, Stack 64, Holex MX150. A lot of good stuff. Yeah. A lot of stuff, good stuff out there. Okay. Well, if there are no more questions, thank you guys very much.